Okay, we're going to get started with our second group here today. Again, just as a reminder for those who might have been here before, this is the second part of the two-part series. They started this a year ago whenever I just gave them requirements of your airplane has to do this, and this. They designed the entire aircraft last semester. This semester, and the reports that you're going to see now are from the test and evaluation portion. So they build the model of their aircraft, test it, validate their design, then modify it and see if the modifications work, then make a recommendation as to what the airplane's first flight test article should look like. So the second airplane that you're going to see, their requirements, I'll let them go over that, but this is an ETOPS-certified, and I'll let them explain to you what ETOPS means. ENDURO.
All right, you got Ashworth. Good morning, everyone. We are ENDURO Business Jets. Throughout the presentation, we will refer to the screen above me as a primary screen, and the screen to your right as a secondary screen. The purpose of the presentation is to go over the wind tunnel testing results of the ER-19 business jet to validate its performance. On the secondary screen is a rendering of the business jet completed in the preliminary design phase, and over here on the right of the table is the final wind tunnel model. I'd like to introduce our team. I'm Morgan Valiant, design team lead. We have EJ Ballesteros on computer work, Jordan Brambit, fabrication lead, Margarita Babinova and Noah Cruzy, fabrication, Hugo Lara as wind tunnel testing lead, and Ali Hess and Chad Penrod on the wind tunnel testing team. On the secondary screen is an overview of today's presentation. We will discuss the theoretical performance of the aircraft, go into the initial wind tunnel testing results. We will discuss the modifications made based on those results, discuss the testing based on those modifications, and make recommendations based on our results. I'll now discuss the motivation for designing the ER-19 and the description of the aircraft. The primary screen shows the appeal to market of a business jet. Business jets save businesses time and money because business jets are able to operate on their own schedule as opposed to the schedules of commercial. Additionally, you get increased mobility because you're able to operate from more airports where commercial airliners only operate from international airports. Business jets can operate from regional airports because they have a decreased takeoff distance. Additionally, on a business jet, you get improved productivity because you're able to work on confidential information for the duration of the flight, and you're able to work the entire duration of the flight without any distractions. On the secondary screen are the current class of these jets. There are the mid-sized jets, which carry 5 to 10 passengers and have a range of 1,700 to 2,500 nautical miles, and due to their lesser fuel weight, can operate from regional airports with short runways. There are also super mid-sized jets, which carry more passengers and go a further distance, but due to their increase in fuel weight, are not able to take off from those shorter runways. In the preliminary design phase, the ER-19 was designed to fill the gap between these two classes of jets. On the primary screen are the specifications for the aircraft. The aircraft was required to take off and land on each 5,000-foot runway, so it can operate from more regional airports, and it had to have a range of greater than 2,500 nautical miles. This range comes out from our request for proposal requirement, or RFP requirement, for an aircraft that can take off from the Pacific Coast states to the Hawaiian Islands, for which the furthest airport on the west coast of the Hawaiian Islands is at Deer Park, Washington, which gave us this range value. Additionally, the aircraft had to be able to cruise a Mach 0.78 with all engines operational, or AEO. On the secondary screen are the mission requirements. The most noteworthy of these is CFR Part 25, which gave us a lot of our design constraints, and our ETOPS requirement, which allows the aircraft to survive an engine out scenario at the critical point in flight to make the transoceanic flight to the Hawaiian Islands. Shown on the primary screen is an aircraft review. The ER-19 features a low-mounted wing, a high-G tail, aft solid-mounted engines, and tricycle landing gear. Additionally, our aircraft has winglets installed on the wingtips that enhance the range performance. On the secondary screen is our ER-19's nose and fuselage. The cockpit was designed to have a pilot and co-pilot with all the instruments involved, and the windshield was designed to give the pilot and co-pilot the maximum field of view. Additionally, we have the cabin, which was sized to hold all 8 passengers, and the conference suite for the passengers, and have enough room for baggage storage and the lavatory. I'll now hand off to EJ to discuss theoretical performance.
Thank you, Morgan. So I'll be discussing the theoretical performance calculated in our preliminary design phase, as well as graphs validating those calculations. On On the primary screen is a requirement verification. So in the second column is our requirement given to us by our RFP. In our third column is the theoretical values that are calculated through our preliminary design phase. And in the last column are the verifying graphs. We'll show you guys later in these slides that will help validate those calculations. The secondary screen is the static stability verification. So in the second column is a stability criteria. Third column is a theoretical value for the stability calculations. And the fourth column are the verifying graphs that I'll show you later to verify those theoretical values. On the primary screen is a theoretical lift curve. So as you can see is the CL max and the alpha stall. This theoretical lift curve will be used later on in this presentation to compare the original test results. On the primary screen is CM versus alpha plot. You can see the ER-19 is predicted to be stable in pitch. On the secondary screen is the CL versus beta plot. The ER-19 is predicted to be stable in roll as well. And on the primary screen is a CN versus beta plot where the ER-19 is predicted to be stable in yaw. On primary screen is a thrust available versus thrust required plots at sea level. As you can see, the ER-19 is predicted to have a pretty large operating space. This is due to the high thrust at sea level. On the secondary screen is the thrust available versus thrust required plots at 40,000 feet. 40,000 feet is where the ER-19 is predicted to cruise. So on the plot you can see that it is able to cruise at Mach 0.78. And if you extend the max range tangent line from the origin, you can see that the max range cruise velocity for the ER-19 is predicted to be 400 knots. The primary screen is thrust available versus thrust required plots at 25,000 feet, one engine inoperative. So if ER-19 were to have an engine failure at the critical point from Deer Park, Washington to the Hawaiian Islands, it would have to descend at 25,000 feet. And you can see that the max range velocity for that altitude, one engine inoperative, is predicted to be 320 knots. On the secondary screen is a theoretical range performance. So you can see the predicted values for the ER-19, all engines operative, and one engine inoperative, does meet the RFP requirements given to us. On the primary screen is specific excess power plots. So the ER-19, so these are operating ceilings that are predicted for the ER-19. And on the secondary screen, you can see the theoretical operating ceilings. So the cruise ceiling for the ER-19 is predicted to be around 50,000 feet. However, the ER-19 would be cruising at 40,000 feet altitude instead. Primary screen is a flat envelope, so the leftmost lines are the scale lines, the top and bottom lines are the load limits given to us by CFR Part 25, and the rightmost lines are Q limits. So those Q limits are derived from thrust available, thrust required plots shown. Up next is Jordan with initial model and design, initial model design and construction.
Thank you, EJ. So in this, in the next slides, I will show you the CATIA model, the fabricated model, and how it is assembled. On the primary screen, you can see our CATIA model. So the CATIA model was scaled down so that it could fit into the wind tunnel. The scaling criteria we used are shown on the screen. And with using these, we got a model scale of 1/24. The secondary screen shows our model exploded view. Note that the orange pieces are the internal steel structure, the blue pieces are made up of ABS plastic, and the red winglets are made up of hard resin. Also, the ER-19 was designed with the ease of assembly for wind tunnel testing in mind. On the primary screen, you can see our fuselage assembly. The fuselage was designed in two pieces so that the internal structure could be easily fit inside. To assemble the fuselage, first the structural block is inserted from the rear bottom of the fuselage. Then the bottom front wing block is inserted onto the main structure, and the back force balance is attached as well. When this is done, then the top of the fuselage will slide on and finish the fuselage assembly. The secondary screen shows the nose cone connection. The nose and the fuselage both have inserts, and to connect them together, they are pressed together and epoxied in place. On the primary screen, you can see our wing assembly. To assemble the wing, first 3 structural rods were inserted into the wings, which consist of 2 16th-inch rods and 1 1/8-inch rod. When this is done, then the wing lid is inserted onto the wing and epoxied in place. After that is done, the wing is attached to the wing blend using the front 2 rods, and 2 set screws are screwed onto the rods to keep them in place. The secondary screen shows the fuselage attachments. We have 2 fuselage attachments, a wing fuselage and a clean fuselage. Both of these are attached to the fuselage from the bottom using 2 screws that attach to the wing block. On the primary screen, you can see our empennage assembly. The first picture to your left shows the empennage with nacelles and tail. To assemble this, there are the internal structural pieces consist of a structural block, 2 1/4-inch rods that hold the nacelles, and 2 vertical rods that hold the vertical and horizontal tails in place. And all of these are epoxied together. The second picture to the right shows the clean empennage, and this just consists of a structural block which is epoxied in place. The secondary screen shows our empennage attachment for both empennage with nacelles and tail and clean empennage. This is attached to the fuselage by both the structural block for the empennage and the structural internal structure for the fuselage are connected together using screws that screw in from the top. On the primary screen, you can see our full model assembly, and the secondary screen shows the other configurations we used. We will be testing with fuselage wing and fuselage only, so that we can see the lift, drag, and moment buildups for each piece of the ER-19. On the primary screen, you can see our model fabrication. The table shows the components, their respective materials, and the process in which they were manufactured. The secondary screen shows our fabricated subassemblies. So there's the clean empennage, the empennage with nacelles and tail, the wing, and the fuselage. On the primary screen, again shows how these subassemblies are put together. The first 2 pictures with the wing and the empennage are put together how I previously stated. And the third picture to your right is the force balance amount, which is what will connect the ER-19 to the test stand. On the secondary screen, you can see our completed initial model. Next, I will be going over the testing equipment and how the velocity determination was done. On the primary screen, you can see the wind tunnel we used. We used a closed-circuit wind tunnel in the Nancy and Tracy Doryland Wind Tunnel facility on campus. This test section has a 32 by 45-inch section. The secondary screen shows our pure middle balance. There is a Velmex motor which adjusts the angle of attack, and there is a beta angle adjustment knob which we had to manually adjust for the side slip. On the primary screen, it shows the tufts we used to visualize the flow on the aircraft. And the secondary screen shows the lighting we used. We wanted to use UV lighting so that the tufts were more easily seen. On the primary screen shows the 3 model configurations, the fabricated models. Again, we used the full configuration, fuselage wing and fuselage only. The secondary screen shows our velocity determination tests. We did 2 tests. The first test was the structural test. In this test, we loaded the wings up until an inch deflection was seen at the wingtips. And with this weight and the lift equation, we calculated a velocity of 118 feet per second. The second test is the aero-elasticity test. In this test, we took the ER-19 and set it to its max angle of attack. Then we increased the velocity in the wind tunnel, and when flutter was seen at 65 feet per second, it was shut off, and since this is the most stringent case, the tests were ran at 65 feet per second. On the primary screen, you can see the center of gravity determination we used. The first picture to your right shows the XCG location determination, and the picture to your left shows our ZCG location determination. The secondary screen shows our full model CG and the ER-19 scaled down CG. Both of these center of gravities were measured from the pin where the moment data will be taken from. Next is Margarita with data acquisition and reduction.
Thank you, Jordan. In this section, I'll briefly go over the data processing inputs and then describe the Reynolds number corrections. On the primary screen are the values that were input into the ERAU software. Note that the locations are positive, however they were supposed to be negative. This was corrected for in the data analysis portion, and all of the values and plots shown in this presentation are using corrected data. The secondary screen shows the model data inputs along with the correct CG locations. The data was corrected by performing a statics moment transfer to get values relative to the correct CG location. On the primary screen describes the Reynolds number corrections. Since we performed low-speed wind tunnel testing, we used post method to extrapolate the data to the full-scale Reynolds number. This gave us comparable values for coefficients of drag and lift to help better approximate the performance over full-scale aircraft. The secondary screen shows the drag polar, with the darker curve being the Reynolds number corrected curve. As you can see, the Reynolds number corrections shifted the curve down and expanded it to the right. Next, I will go over the force and moment data from our initial test and compare them to theoretical values. The primary screen shows the seal versus alpha plot, showing the theoretical lift curve along with the curves from our initial tests, both uncorrected and corrected. We observed premature stall, with the stall region starting about 10 degrees, resulting in a lower seal max than predicted. The secondary screen shows flow visualization of our model at 10 degrees angle of attack. The separation seen at the wingtips confirms the onset of stall at this angle. The primary screen shows the CD versus alpha plot, with the darker curve being the Reynolds number corrected curve, which resulted in a parasitic drag coefficient of 0.029. The secondary screen describes the major drag contributions that we observed in our initial test. We saw a separation on the nacelles and the empennage upsweep starting at 0 degrees angle of attack onward. Another major drag contribution comes from wind tunnel testing limitations. With no engines in the nacelles, flow through them produces a large amount of drag that would not be seen in actual flight test. The primary screen shows the CM versus alpha plot, showing the theoretical along with the curves from our initial test. As expected, the fuselage-only configuration is unstable. The fuselage wing configuration is stable up until the stall region, and with the addition of the empennage, our full configuration is stable up until the stall region. And again, on the secondary screen, you can see a separation starting at 10 degrees angle of attack, which is where we become unstable. The primary screen shows the seal versus beta plot from our initial test. All three configurations are unstable in our initial test. With no engines turning up in the nacelles, float and angle beta produces a large thrust drag force on the inside, and with their position above the CG, this produces a destabilizing roll moment. On the secondary screen is our CN versus beta plot from our initial test. The fuselage only and fuselage wing configurations are unstable. However, with the addition of the empennage, we are stable, but not as stable as predicted, likely due to sidewash coming from the nacelles onto the vertical tail, reducing its performance. The primary screen concludes our static stability verification. From our initial test, we are stable in pitch up until the stall region. We are unstable in roll and stable in yaw. Next up, Chad will go over initial performance verification.
Thanks, Margarita. So in this section, I'll be going over a little more of the test data and comparing it to our theoretical values. On the primary screen, you can see the thrust available, thrust required plot at sea level. Again, due to our increase in drag, you can see that the thrust available line shifts up, limiting our operating space. On the secondary screen, at 40,000 feet, you can see another thrust available, thrust required plot. Once again, due to that drag, our operating spaces decreased, and with the tangent line coming from the origin, we found a max range speed of 325 knots. On the primary screen is the thrust available, thrust required plot with the one engine and operative scenario at 25,000 feet. Once again, due to the drag, our operating space is limited, and we calculated a cruise speed of 210 knots. On the secondary screen, we calculated our range performance from these plots. With all engines operative, we found that our initial model calculations had a range less than our theoretical values. Same thing with our one engine operative scenario. However, we still met the range requirements. On the primary screen is a theoretical piece of S plot, and for comparison, we have the experimental piece of S plot on the secondary screen. As you can see, due to the increase in drag, our ceilings were reduced, and once again, our operating spaces were constrained. On the primary screen is our theoretical flight envelope, and for comparison, we have the experimental flight envelope on the secondary screen. Due to the reduction in our CL max, the stall lines shifted out to the right. The load limit stayed the same because those are from our CFR Part 25 requirements. And from the thrust available, thrust required plots, as I previously mentioned, our Q limit shifted to the left. So in summary, the performance verification from our initial tests, we found that our takeoff field lengths and our landing field lengths increased. However, we still met the requirement of 5,000 feet for both those field lengths. As I mentioned previously, the range requirements were met for both all engines operative and one engine operative. Our cruise speed was calculated to be 0.63 Mach, and our requirement was 0.78 Mach. And on the very bottom, you can see our calculated CD naught value. So from our initial test, we evaluated our data. We found that we were stable in pitch up until the 10 degrees stall, and we found that we were completely stable in yaw. However, we were unstable in roll. We had significant regions of separation, both on the nacelles and the upsweep of the empennage. And we found that our wing performance was lower than we predicted. So from these evaluations, we had some recommended changes. We had 5, but we were limited to 2. We wanted to refine our nacelle geometry to reduce that separation drag on the nacelles, and we wanted to add ventral strakes for 2 reasons. Those 2 reasons being to reduce the separation drag from the empennage and to contribute to our roll stability. Up next, I'll pass it off to Noah Cruzy for modified model design construction.
Thanks, Chad. So over these next couple slides, I'll be going over our modified model changes that we went with and how we designed them. On the primary screen is our refined nacelle. You can see our initial design nacelle and our modified nacelle. The initial nacelle, as you can see, has a very steep angle at the front towards the inlet, and this caused to have that separation drag that we noticed in wind tunnel testing. We have to accommodate the power gear or the engine's gearbox on that lower part of the nacelle, and so we decided to shift the engine back to allow for a more gradual taper of that nacelle to improve the overall aerodynamics. And on the secondary screen is the completed nacelle on our new model. On the primary screen is our second change, the strakes. We based this off similar aircraft. We looked at the Beechcraft B200 and the Learjet 70. Again, as Chad previously stated, the strakes were for 2 purposes: to help reduce the separation drag on the empennage as well as improve our lateral stability. On the secondary screen is our strake parameters. We have the wetted area and the angles that we chose. We chose to have a larger anhedral angle, and this again is to improve that lateral stability. On the primary screen is our model modifications. We have the refined nacelles on the new empennage, and we have the ventral strakes. We also put the ventral strakes on the clean empennage. This was so that we could see how the performance, how the performance was affected by the strakes on the aircraft in all configurations. And on the secondary screen is our modified model fully assembled. Now I'll be going over the data that we received, or we got from the wind tunnel, the forces and moments. On the primary screen is our CL versus alpha plot. Our initial test is in blue, and the orange test, our final test is in orange. As you can see, they are very similar. We did have a slight loss in CL. And on the secondary screen, you can see our aircraft stall region from 10 to 12 degrees angle of attack. On the primary screen is our wing stall at 12 degrees angle of attack. As you can see, the wing stalls at the tip first, which is expected for our wing design. We have a aft swept wing and a high taper. On the secondary screen is our wing stall at 16 degrees angle of attack. And as you can see, the stall has moved more inboard now, which again is expected for our design. On the primary screen is our CD versus alpha plot. The blue line is our initial and the orange line is our modified test. As you can see, we did have a slight increase in drag, and this is due to the strakes on the empennage. On the secondary screen, you can see the ventral strake vortices. So starting at the bottom, we did see a vortex introduced, and it does move up the strake. However, due to a high pressure region at the top of the empennage, these vortices were pushed outward, and as you can see, it resulted in that loss of the vortex at the very end of the strake. On the primary screen is our new nacelle flow, and it is actually attached. We observed this at a 0 degree angle of attack. And on the secondary screen is our new nacelle when it's separated, and this was observed to start happening at 20 degrees angle of attack. And this is likely due to downwash from the wing. On the primary screen is our CM versus alpha plot. Note that all the darker colors are our modified model, and all the lighter colors are from our initial test. We did have a shift in our CM knot value, and this is because of that strake. It produces a pitching up moment. We also have that stall region. The aircraft is stable up until stall occurs, and this is because the aerodynamic center of the wing is aft of the CG of the entire aircraft, and as we lose the lift during stall, the wing no longer has that stabilizing effect on the aircraft, and the empennage is not large enough to counteract the destabilizing effect of the fuselage. On the primary screen is our CL versus beta plot. We are still unstable, however, we did see an improvement in the stability, and this again is due to the strakes. And on the secondary screen is our CN versus beta plots, and nothing has changed here. On the primary screen is our static stability verification. We are stable in pitch up until that stall region when we become unstable. The lateral stability, we are still unstable, and our directional stability, we are still stable. Next up is Hugo, who will be going over modified performance comparison.
Thank you, Noah. Next, we briefly comment the contribution of the refined nacelles and the ventral strakes to our aircraft's performance. On the primary screen, we have thrust available as required at sea level. As we can see from the bold line, that's a modified model. The increase in drag has actually reduced our operating space and our specific excess power. On the secondary screen, we have thrust available as required at our cruise ceiling, 40,000 feet. Again, the same trend transpires to this altitude, with our modified model having more drag and reducing operating space. Here we have the stall speed identified at 201 knots and a max range speed at 310 knots. On the primary screen, we have the thrust available as required at 25,000 feet for one engine inoperative. Again, as before, the modified model had more drag, reducing our operating space. We have a stall speed here at 115 knots and a cruise speed of 108 knots. It must be noted that the modified model was not able to meet the range requirement for one engine operative for ETOPS at this altitude. So, ENDURO business jets looked into other altitudes to satisfy the requirement. However, the modified model was not able to achieve this. On the secondary screen, we have the range performance for all engines operating and one engine operating. As we can see, compared to the initial model, the modified model had a reduction in ranges for both all engines operating and one engine operating. On On the primary screen, we have the initial model specific axis power plot compared to the secondary screen, the modified model specific axis power plot. Again, same trends from the increase in drag. We have lower our ceilings and a lower operating space. On the primary screen, we have the experimental flight envelope for both the modified in red lines and the initial in blue lines test models. Again, due to the increase in drag, the cumulants were actually shifted to the left, producing our flight envelope. On the secondary screen, we have the performance verification for the initial model compared to the modified model. As we can see, the takeoff field length and the landing field length, both these values are increased from the initial model to the modified model due to the increase in drag and the reduction in wind. Our ranges, again, for all engines operating and one engine inoperative for ETOPS were both reduced for the modified model, and our cruise speed was also reduced compared to the initial model. As we can see, this mostly contributed to the addition of ventral strakes, which did not benefit the aircraft for its requirements. Next, we have Ali with structural design and analysis.
Thank you, Hugo.
I will now be going over the structural sizing for the wing and horizontal tail of the ER-19 and the analysis that confirms the sizing choices. On the primary screen is the load approximations for the wing of the ER-19. This load was approximated assuming that the wing would take on the full weight of the aircraft. A load factor of 2.84 and a factor of safety of 1.5 were used. This load was assumed to be a distributed span-wise load, and was estimated using the strengths approximation. On the secondary screen is the load approximation for the horizontal tail. This load was approximated to trim the aircraft during cruise, causing a nose-down pitching moment. The same process was used to estimate this load. On the primary screen is the wing sizing. A moment solution was used in order to determine the percent load on the forward and rear spars. The spar caps, which are the shaded regions, were sized to take on bending of the wing. The shear webs and skin were sized to take on shear. An open and closed shear flow analysis was performed by hand at first, and then validated later using ANSYS. The secondary screen shows the horizontal tail sizing. The same process was used to size the structural components. On the primary screen is the finite element model of the wing. This wing box was section that was analyzed is the wing box at the fuselage wing attachment point, which is where the highest stress is located. 4 distributed wind loads were put on the free end of the wing box to simulate the shear at this location. The rib size and rib depth in the Y plane, the Y axis, is 24 inches, which is our rib sizing. The secondary screen is the finite element model for the horizontal tail. This wing box is at the vertical tail attachment point, again, the highest point of stress. And the same process was used to mesh this. On the primary screen is the model solved for shear in the YZ plane. Notice the max shear is at the forward spar at 26,600 psi, and the skin sees almost no shear, which is expected. On the secondary screen is the finite element model for the horizontal tail, solved for shear again in the YZ plane. The forward spar takes the max of the shear at 8750 psi, and the skin again takes almost zero shear. On the primary screen is the model solved for compression in the Y-axis. The spar caps were sized to take on most of the compression, which is expected and seen in this solve. On the secondary screen is the horizontal tail solved for compression in the Y. Again, the spar caps were sized to take on all of the compression, and they did. On the primary screen is the wing structure validation. taking the materials selected for each of the components and their allowable shear. We compare that to the predicted shear that ANSYS predicted, and in each of these cases, for each component, they are not predicted to fail. We chose aluminum alloys for each of the components for its high strength weight ratio, high durability, and resistance to corrosion and fatigue. On the secondary screen is the horizontal tail structure validation. The same process was used, and again, none of the components are predicted to fail. On the primary screen is the fuel storage for the ER-19. There are wing tanks, which take most of the fuel, and a forward auxiliary tank, and then a settle tank behind the wing. On the secondary screen is the fuel storage in gallons for each of the components, and then the total fuel of 1309. Next, I'll pass it back to Morgan for the market analysis.
Thank you, Ellie. I'll now discuss the cost of the ER-19 and the lifecycle cost of the aircraft. The primary screen is the cost of the ER-19. The price of one unit is about $18 million, and our RPO requirement was to make the ER-19 a cost-effective aircraft for a 200-unit purchase. With a break-even point of 94 aircraft, determined with our market analysis, we found that the ER-19 is a cost-effective aircraft to produce based on our results. On the secondary screen is our lifecycle cost, assuming a 20-year life cycle. Included in this analysis are the fuel costs, crew costs, and other direct and indirect operating costs as shown. I'll now discuss our team's labor hours and labor costs. Primary screen shows our team's labor hours. The blue line indicates our planned hours. The team planned to have 2 hours worth out of class in the project for every 1 hour spent in class. Additionally, we have the orange line, which is our actual hours spent on the project this semester. Note that even though our hours are below what was planned in the semester, we still completed all the tasks involved. On the secondary screen, the team's labor costs, with the most notable being the technical work and engineering work. I'll now discuss our team's conclusions and recommendations. ENDURO concluded that more modifications are needed to improve the roll stability of the aircraft and decrease our drag to enhance the aircraft's performance. Additionally, the strakes had little effect on our roll stability and were shown to increase our drag. Our nacelle design did not have high separation until high angles of attack, as opposed to our initial design, and our wing and horizontal structures were sized and validated by an element analysis to take all the loads of flight. ENDURO recommends for a flight test article to exclude these strakes as they did not improve the performance, and to include the new nacelle design because separation was not shown to occur until high angles of attack, which is an improvement over the initial models themselves. Additionally, ENDURO would like to continue wind tunnel testing on features that may improve the performance of our aircraft. These include vortex generators in the upsweep, to reduce the upsweep separation noted during testing, to include vortex generators in the wingtips, which will reduce the onset of stall, to elongate the aft fuselage section, which will decrease the upsweep, delaying the onset of separation. This will also allow us to move the tail aft, which will increase stability and move the vertical tail out of the wake of the nacelles. To increase the tail size, which will enhance our stability overall, and to move the nacelles further out from the fuselage to reduce the interference drag between the outside of the nacelle and the fuselage wall. I'd like to thank everyone for attending our presentation. We'll now open the floor for questions.
Okay, good. Got a few minutes for questions. I'm going to start on the back row this time, so Kenny gets first shot at it, since he's still busy.
Great job again, you guys. Yeah, I have no idea. Other than saying good job, I remember being in that seat, in that position. Quick pointer out there on slide 66. You guys were highlighting your material dimensions and skin caps. Just kind of question, comment. How critical is that 0.5 inch there? You go all the way up to 4 decimals on the point there. So how critical is that to your design?
That's an excellent question. I will pass it on to Hugo Lara.
So the 0.5 of an inch The skin you're meaning, right?
Yes.
We size all of these to the nearest gauge for manufacturing. So these are all expected fractions, so that's why we have that call out. But there are gauges. So
Right, yeah, so standard manufacturing sheet metal thickness is what you write, but typically on a drawing spec, just go to 63. So just kind of a semi-trick / softball question for you, but in reality, how critical to your design is that 5/10 of an inch? Right. So just bear in mind when you throw up those dimensions in there. On a computer screen, 5/10 of an inch can look like a football field, but if you were to take a caliper and look at 5/10 of an inch, you're less than the sheet of thickness of paper. Okay, so just put that in perspective. I've had my run around quite a few design engineers on seeing little digits like that. Okay.
Clarification, 5/10,000.
Correct, 5/10 of an inch, 5/10 thousandths of an inch. Half an inch is rather large, yeah. Okay, so you guys may hit upon it on the recommendation, slide 75. Looking at the labor hours here. So you guys, if you were to glance at slide 75, you could almost say you exceeded your budgeted hours, right? You're about 230 hours, just under what you anticipated. Given the fact that you guys put in your nacelle strakes, and seeing how they didn't quite measure up, do you think you guys had enough time to go back in there and do another analysis to see what other improvements could be made for your goals to build?
Okay, so the main detractor from our labor hours from our initial design phase, where we constructed our fabrication plan and testing plan. After that, as noted by the March 4th date on that plat, after that we stayed roughly constant. So we were done initially by making our initial model, but then we picked up afterwards to continue with the project. So,
We were only allowed to do 2 tests, given by our teacher.
Only gone to town twice.
All right, good job, guys.
We scheduled tunnel time, but you know how expensive that is.
All right, go back. You guys did an excellent job. Nice job, work doing it. I have a combined question between 52A and 63B. Your performance verification, talking about your field lengths, particularly after you finish your model, that's been pretty close to what your requirement was. Then thinking to your seal max curve, your seal maxes were considerably lower than what you predicted in the first place, which is part of what drives your predicted field lengths to much closer to what your requirement was. The question is, did you consider a flap setting in those field lengths, or is an allowable configuration for either takeoff or landing?
yeah, so I can answer that question. So for the takeoff field length, we excluded the use of flaps, just so we verified our total takeoff field length based on our requirements. Additionally, the landing field length assumed the use of thrust reversers to reduce the overall landing field length based on our requirements. And the use of flaps, yes. Landing flaps.
So you made seal adjustment estimates for the flaps down configuration for the landing field length?
Yes.
The adjustment, okay. One comment there in general, details are very prone to a deep stall and are common to have stick pressure devices installed in them. What that's going to do is it's going to take your seal max value up there and it's going to shift it even farther left, because your warning and activation of that system are going to have to happen at some point prior to your aerodynamic stall, which then makes those numbers even worse. Something to keep in mind down the road as a realistic aircraft system will try to design.
Okay.
Thank you.
Good work. I suppose it may be moot because you've got an unstable roll, but have you got any predictions on your neutral and spiral modes?
We did not include any dynamic analysis due to the time constraint of the course. But in the future, if we were to continue the analysis of aircraft, we would include the dynamic stability analysis of aircraft.
Okay. So a couple of other comments. I mentioned this to the last team, and I'll mention it again in case you missed it, but anytime you show some type of a like a C in beta plot or a C in alpha plot, you have to include the configuration there with the plot, because that plot will get pulled and used out of context by somebody else without you knowing at some point. So always make sure you do that. Go back to slide 10A. I loved this where you showed your thing and then your verifying graph. That's an excellent way to do that. I'll get pages of requirements that I have to show that I need. And doing it like this where you can just point to, okay, go look at this plot, it proves it. Go look at this plot, proves it. That's a nice way to do that. I like it. 46B. You mentioned, am I in the wrong one? 46B. Yeah, you said you're only allowed to do two things. Was that imposed on you by your management? and you hated him.
I let them pick the two.
I just wanted to say, this is real. It is so real, because you're gonna wanna do something on your design, and your management's gonna go, no, you can't do that, and you're just stuck. So you may have hated him for that, but I'll tell you, it's real, and it's gonna happen.
Thank you.
I got a couple of quick things. One, your wind tunnel documentation was probably the best I've seen. I've seen a number of the wind tunnel tests go, but your documentation and explanation was outstanding, so kudos to you guys for doing that. Your ETOPS predictions, you're really, really close to the margin on that. One question I have, and I don't know, I was just wondering, is the ETOPS requirement a no-wind condition, or are you supposed to meet your ETOPS in some kind of nominal headwind condition?
It is without the use of the wind condition, but
Yeah, so basically worst case scenario is going to be no wind, because if you're at the critical point and there's no wind either direction, that is, because if you had a tailwind, you probably just continue flying to Hawaii. If you had a headwind, you turn around and head back. So no wind is the worst case scenario.
Okay, all right, okay. And that's all I have.
thank you.
All right. Well, once again, you guys did a great job, really good presentation. I got a few things. So this was a question I had for the last team, but I didn't get to ask it. When you talk about ramping up the wind tunnel speed to AC flutter, where exactly are you seeing it? And what are you seeing?
That's a good question. I'll look for that question to George Graham.
So when we ramp up the wind tunnel and flutter scene, where we saw it was on the wings. And did you say what were we seeing?
Yeah.
So just wing moving like this?
Okay. I was curious because I think I've seen stuff before where the whole thing rocks, and that's something a little different. The last team was saying they had it on the wings and the HT, and rarely get it on both at the same time. I was just curious what you guys were looking for. Another question I had was, so go to slide 6B. So, they looking at, there's a really common saying, if it looks right, it flies right. And looking at the first thing I thought when I saw the tail was that's way too small. And the results kind of showed that. And I was just curious why you decided to add strakes rather than explore. It looks, you've got two jets with tail farther back, nacelles farther down and forward. They've got some dihedral on their HT. I was just curious why you didn't explore further options with your empennage and went for those strakes for real stability.
Okay, so for the first part of your question, we sized it based on methods we had during our preliminary design phase, and we just carried that on to the missile testing. Additionally, we tried to use the design of the strakes to also reduce the separation around the M sweep and to enhance the lateral stability. So we tried to get the best of both worlds with the strake design, as it is with a similar aircraft.
Okay. I think I'm just going to leave it at that. You guys did a really good job. Thanks.
Thank you.
Yeah, this was really excellent work. Thank you guys for working hard. I do want to ask a little bit more. So 46B, and it's a little kind of piling on to what Bryce said and a little bit to AJ. I had to, actually, I Googled the equation for CL beta. Where, did you consider changing the wing sweep? And why not? Or why did you?
So we did consider alternative wing design, including our wing sweep. However, by reducing the sweep, we would have reduced our CL max, which would have increased our takeoff distance.
Right.
And during testing, it would have most likely validated our requirement, or not validated, violated our requirement, I should say.
Okay.
So we did look at that, but we tried to not change the wing too much, because if we did, we would change the location of the aircraft, or aerodynamic center location of the aircraft. So we wanted to try to minimize as many changes as we can.
Okay, so that change was going to affect too many factors, is what
Yes.
you're saying. Okay, got it. And then, let's see, as far as, let's just talk a little bit about kind of the end user experience, so I'll call it that. What do you expect the stall to be like? In terms of if a stall occurs from the cockpit, what do you expect that to be like? Sudden, abrupt, pitch up, pitch down, scary, not scary? Talk to me a little bit about kind of the handling qualities that you expect.
Well, based on our CM alpha plot, one thing we noticed is that during the stall region, our aircraft became unstable. So in the event of a stall based on our results, in the cockpit, the pilots would notice a pitch up moment as alpha increased, which is an unstable case. So we did make recommendations to improve our tail design, such as elongating the fuselage, moving the tail back, increasing the size, which would have most likely made the horizontal tail more effective in making it stable after the wing stalls.
Sure. Okay. And then as far as the onset, do you expect it to be a sudden or an abrupt onset stall?
Based on the Reynolds number effects for a full effect test, it would most likely be more abrupt than what we saw. What we saw in the current test is very gradual based on Reynolds number.
Okay, let's go to 52 item. So what I see is that the curves bend over really gently. And based on that, what I'm seeing is as you increase alpha, your CL is only changing a little bit, which to me says it's actually going to be a little bit more of a gradual onset. But what really you're going to get is you're going to get that abrupt pitch up. So you'll kind of get a loss of lift, but you'll really get it'll get your attention pretty quickly with that. And I think that kind of piles on to AJ stole my point about stall protection. You're going to need something because that's traditionally, a lot of folks they do a lot of their training on straight wing. Straight wing usually stalls nose down. Straight wing stalls nose up, which is going to get you. So yeah.
Piggyback something there real quick. The certifiable requirement for pitch is nose down. So when you hit that nose up region, that's uncertifiable pitch anyway, which is also probably what's going to drive you to a stall protection system.
Perfect. Thank you. Yeah. The only other question, 57A, and then we'll get off the stage. What is going on with the fuselage wing modified? I understand you guys only did points every 2 degrees of beta, but I can't make heads or tails of what are the wild points and what is quote unquote real. If you had more time, what do you do about the red line?
So it is a noticeable error figured during testing, just the experimental error with our model inputs, perhaps.
Okay.
But we did the trial validation, and we figured out that it was actually the same for both tests. Because we were able to do 2 tests because the ease of assembly of our model allowed us to do 2 trials for every single test at every single configuration.
Oh, that would have been good to say. Something about confidence in your model, something statistics. That would have been really great to say. And then, that's something that, in past at Edwards that we're real big on, is being able to talk about confidence. Even if you only do it once and you can say we have 50% confidence, which is not great, at least you can acknowledge that and you can acknowledge the risk to the customer. Look, hey, if you give us more money, we can give you more confidence that this is or is not the answer. That sows a lot of doubt in people's minds. Awesome. All right, thank you guys.
Thank you.
Yes, great job. Love the completeness of the material presented and some of the extra documentation and kind of explanations that you guys gave. So that was very well. So I'll go to slide 56 and we'll talk about the pitching moment coefficient here. So one thing I've noticed on this chart is your CM naught value, especially from the initial to the modified, right? So there are two things different there. There were the strakes and there was the nacelle, correct? All right, so why did your CM naught increase so much? Because that's a pretty drastic change if you look at it relative to where the initial model was. So let's talk about that.
Okay, is there a question? I'll defer that question to Narcoozy.
So the strakes create the pitching up moment. Can you remind me a little bit more of the question?
Sure. Okay, so there's two things that can cause this, right? The strakes or the nacelle.
Yeah.
So this is a CM naught value, so there's an offset in your essential zero lift pitching moment.
Yeah.
So why did that happen?
So it is the strakes, and that's because, so on all of our configurations, the fuselage only, there are no nacelles. The wing fuselage, again, there are no nacelles. So since all of those have that shift, it's strictly just going to be the strake that is causing that pitching moment.
So it's believed that the strakes, they have lift that is produced going down, which makes that pitching up moment, making the CM naught shifted up.
Okay. Yeah, so this is something we deal with CM naught, right? So we talk about where's our aerodynamic center, and then we talk about basically how big is the lift at EAC, right? Those are two things we have to trade off. So moving on from that, is that an issue for you guys down the road? If so, why not?
Yes, so one reason for that is not something that is favorable is increasing the value of CM naught also increases our stall angle of attack, or not stall angle of attack, our trim angle of attack, which will increase drag.
Yes.
And that's why we also recommended that to execute these restrictions for that reason as well.
Yeah, so that's right on the money. So the next step would be, you guys thought about it, so can you tell me about that? You know, when you present these charts and stuff, maybe you guys did and I missed it, but just kind of having that extra step of, oh, hey, by the way, we know this is going to impact our trim. We didn't do any trim analysis yet, so we're going to down the road. And to kind of piggyback on that of what Scott mentioned with the dynamic analysis, there's some very easy calculations and assumptions you guys can do with the equation of motion when you do have these coefficients to actually calculate when we talk about unstable. So we talk about the Dutch roll. You can actually calculate what your time to double is, and that's going to come up when you develop your control laws as well as commercial aircraft. So I don't know what certifiable, what some of the limits are, but you know, some of the aircraft I work with, it's just a matter of can we still control it? Is that okay? So just kind of some extra points on that. Real easy to make that extra step and kind of take it to the next level. Great job.
Thank you.
Yeah, great job, everyone. Really well put together presentation. Just to reiterate what you said, that table on slide 10A, I really like that, the one where it shows, it's kind of taking the requirement and showing the validation verification process all the way through and where to find all that, so I really enjoyed that. Slide 53A, please. For your wing stall, does this not concern you guys that much? That it stalls from the outboard? I know you said that you expected it, but does this not really concern you as much as some of the other things?
Yeah, so it is concerning because it would cover most of the area of the ailerons in this situation.
That's my main concern, especially since you're already roll and stable, and once you hit stall, you will lose almost all roll control. So that was my main concern. But I'm glad you stated that you will lose most of your ailerons, because that is concerning. Slide 71A, please. So for your fuel in your wing tanks, are you planning to put fuel in like the entire length of your wing like that?
That was an excellent question. I will defer to Sheila.
Yeah, we're planning on filling the wing as much as possible.
Okay.
We tested it to out just before the aileron began on the wing, and we needed more volume, so that's why we spent it out a little bit more.
Okay. The only thing that concerns me there is unless you have a very heavy and costly pump system, you're likely going to get trapped fuel in some of those tanks as you're switching between the ribs. So as the flight controls will tell you, they'll probably have to try to account and for all that changes as you're flying. But with that, you'll also, so it'd be pumps that you would have to add weight to and fuel probes to make sure you know how much fuel's in each section of that wing. So just be mindful of that. I know it's something you probably didn't think of in this kind of design process, but that is something that you might want to look at. Otherwise, great job, everyone.
Thank you.
All right, we're pretty much at time, so I'm gonna keep mine down to 1. Can you go 73? So with your life cycle costs, what are you anticipating as the actual flight cycle for the amount of flight hours that are attributed to 20 hours of flight?
That's an excellent question. I will defer that question to Cruzy.
It's been a while since I've really looked at it, because like we calculated these in the preliminary design. I was using Rushton's text, and there's just like a Raymer, yeah. So Raymer's text, and he has just kind of a step-by-step of like what hours generally for a like a business jet or a private jet type scenario. I don't remember those off the top of my head, but we have those numbers.
So that actually answers my main point, which is state for yourselves, to remind yourselves, and state for us what your assumptions are. So that would be really nice to see, so that we understand the kind of actual duty cycle of the airplane, and can see if I'm expecting to get 50,000, million, whatever, however many hours. Thanks, good job.
Thank you.
All right, thanks, guys.